Hey Caitlin, how's it going? Today we're going to cover the mediation model as we kind of discussed in lab. So just diving right into things, we are going to be looking at this Jupyter notebook on the left. You'll have access to this file and you can run it in the cloud, or you can copy the code into your own R environment. And then we also have some notes in the top right hand corner here. So when we're talking about a mediation model, where usually, we start off with an independent variable and a dependent variable. So an independent variable x here, and then there's some effect on y. So in this instance, we have the example of negative affect being affected by neuroticism. People that are highly neurotic tend to have a lot of negative emotional feelings, right? And as a psychologist, you might hypothesize or theorize that the mechanism or how this works is because the person is always really tense, right? If you're neurotic, if you're high in neuroticism, as a personality trait, you are tense all the time, and then that gives you the negative emotions. There's a mechanism, a mediator through, a mediator that kind of intervenes these two variables. So there's a lot of other examples classic examples you can look up, like stress affecting depression through the loss of social support. If you're overly stressed, you won't seek out as much support because you might be isolating and withdrawing. And there's more and more examples, but mediator models are very classic methods in psychology. So we have the kind of a theorized model here. You have the equation in the notebook on the top left-hand corner, but just in diagram form, we have neuroticism, which affects negative affect through tenseness, right? And so we estimate three regression coefficients. We call them A, B, and C. We can see them, as such. And these three regression coefficients give us the direct effect, C prime. We call that dash prime. And then the indirect effect, which is calculated as A times B. And then the total effect, which is just the regression coefficient if you were to regress negative affect on neuroticism, right? That's the total effect. So we can kind of break it down, the total effect that we found, into a direct and indirect effect. And a question you might ask is, well, what percentage of the total effect does the indirect effect make? If it's like 1%, then this variable doesn't really matter that much. Whereas if it's 100%, you might say that that's full mediation. This relationship between neuroticism and negative affect is fully mediated by tenseness, right? So it's probably somewhere in between for all, intents and purposes in psychology. It's usually partial mediation we're working with. So, the questions that we usually ask are, is there a significant indirect effect that we can detect, that A times B path? And then what percent of the total effect is mediated by M? So you can calculate that by, doing the indirect divided by the total. So there's two ways to kind of get at this 95% confidence interval to get that p-value, right, whether it's significant or not. The classic way by Barron and Kenny from 1986, cited tens of thousands of times. We have the Sobel test. We calculate standard error and a 95% confidence interval using that formula. The more modern method is through bootstrapping, which essentially, let's say you have a data set of 1,000 observations. You sample from that data set with replacement, and then you refit the model. And then you'll get your A, B, and C once. It's a little bit off from your original data set because you resampled, right? You treated your sample as the population, and then you sample from that, and then you fit the model. You get A, B, and C, but they're a little bit different. You do that once more, and you essentially you do that B times, let's say 5,000 times is the typical amount, and then you get an empirical distribution of your coefficients of the A times B, and then you take the 2.5 kind of percentile number, and then the 97.5 percentile number, and then that's your empirical bootstrapped indirect effects 95% confidence interval. So diving into some code here, in the top right, we're going to use a software called lavaan. So in the Jupyter Notebook, we first install some packages. Right, lavaan is right up at the top, alongside some other helper and visualization packages. We load in the data. You can just use the through the psychTools package. You can use data MSQ, and then you get this. You can get this data set from psychTools. I'll refer you to their psychTools documentation for what the data set's all about. But essentially, you get a whole bunch of variables. You can see neg-aff is for negative affect or negative emotions. Let's see if we can find the other ones here. Tenseness, tense, and then neuroticism's near the bottom here, right? So you can run some descriptive statistics and find out what those are all about. But we're just going to dive right into lavaan and then use this structural equation modeling software that's really popular in psychology and fit this model using this syntax. So I've got the abridged version in the top right-hand corner. Essentially, the first line reads, tense is predicted by neuroticism, and we get the A coefficient. Negative affect is predicted by tense arousal. That's TA, I suppose. Tense arousal. And then negative affect is predicted by neuroticism. We get our 3 regression coefficients, and we're good to go. When just as a note, you might say like, oh, these 3 models are not saying what the diagram was. lavaan automatically makes this kind of combines these two to form. Let's see here. Combines these two to form partial regression coefficients. So you can write them as separate lines, but then lavaan under the hood combines them so that you get partial regression coefficients. Just a side point. So you can see in the code here, we fit the model using the SEM function from lavaan. We put our model in there, and we get data equals MSQ. This will yield you I believe the Sobel test coefficients. I think, we can run a summary with, and then we get a data table here. So you have your A, B, and C coefficients. You can read this table by the, tense is predicted by neuroticism, so that's your A path. You get your understandardized regression coefficient in the EST column, standard error, Z value, P value, confidence intervals, and then these are regression coefficients that are kind of standardized in different ways. STD LV is you standardize the latent variable. This is the same as the EST column since we're not working with latent variables. STD all is when you standardize everything to become correlation coefficients. So that's actually a column you might want to pay attention to. And then standardize.NOx is when you standardize everything except for exogenous variables. We're not going to work with that here. So std.all, standard all, and EST are essentially correlation coefficients and unstandardized regression coefficients, which both are good to report. So we just verified here, Sobel test, the A times B is your indirect effect. That's what we're really more concerned about. And then the Sobel test yields a standard error of 0.0069 and its own confidence interval. We verify that through the Sobel test kind of math that's 0.0069. But we don't want to use the Sobel test. We want to do bootstrapping. So here's some of the math. We essentially, resample. So we create B new samples. We won't dive too much into the notation here, but essentially we have our original sample X, but then we create 5,000 new samples. We create new 5,000 new samples by sampling with replacement. Then we calculate our A, B, and C each time. So we fit like 5,000 models. We get A, B, and C 5,000 times. You can calculate a standard error if you want, but then right now we're mostly concerned with the empirical distribution. Once you sort the coefficients A, B, and C, or A times B rather, then we can get at the 2.5 percentile and the 97.5 percentile, you can get your empirical confidence interval like that. So in the end, we end up getting our results, our table here. You can see that we have a standard error of 0.0074 and then a slightly different confidence interval than above. But to be honest, it's quite similar in this case. Point estimates should be largely the same. So these are just some charts showing off the empirical distribution. It's actually fairly normal with a bit of skew in this case. And then more visualization code and table code, so we can see some numbers here, and these numbers are reflected in the top right-hand corner, where we have a 0.2 as an A effect, nearly 0.4 as a B effect, yielding roughly a 0.07, just below 0.08, yielding about a 30% indirect effect. Percentage of the mediated, if you do indirect divided by total, right? So we have, and these are all significant effects. So in short, we have partial mediation. The relationship between neuroticism and negative affect is partially mediated by tenseness and tense arousal. Tenseness captures around 29.5% of the total effect, and you can also report the R squares, where the negative affect explains 32.7% of the dependent variable, whereas tense arousal explains just about 4%. So, or rather, maybe I have to check this, but I think the independent variable explains 4% of the mediation of the tense variable, and then if you use X and M to predict Y, you get about a 30%, a 0.3 R square, which is pretty good. So that's, a basic mediation analysis. There's a few assumptions that we kind of make along the way. Just going through them very quick. No unmeasured confounding. So if you have third variables, then you're by creating this structure, you're saying this is the truth, and you have no variables outside of this structure that you haven't measured. It's quite a difficult assumption to meet. Correct temporal order. So if you measured, let's say you measured tenseness like 2 days before, it's not theoretical. In that instance, it's not possible for your neuroticism to cause your tenseness unless you're assuming its personality. In that case, is always stable, and it would have been that way. But in general, you have to have the mediator happen after, and the outcome happen after that. So there has to be a correct temporal order. We're assuming lines, linearity. That's how we can get the A times B is the indirect effect, and how it adds up nicely. C prime plus A times B is equal to the total effect. We're assuming linear relationships. That's not always the case. Could be curvilinear, could be an interaction. Speaking of interactions, there's no interaction between the independent variable and the mediator. A lot of times, these two variables, if you're higher in neuroticism, it might change how tense you are, or if you're lower on neuroticism, it might affect the level of tenseness you might get. and that relationship may not be static, right? There may be a complex interaction there, and this structure assumes no interaction. And then, as usual, reliable and valid measures. So then, if your X, M, and Y are not reliable or valid, then you could get biased results. So anyway, we'll call it there. That's your basic classical mediation. You can read up Barron and Kenny, 1986, for the classic paper that's been cited tens of thousands of times. And then there's also David McKinnon, 2008. That's a pretty good paper as well. So we'll kind of leave it there, and then have a run through of the notebook when you get the chance, or plop the code into your own R script. Thanks a lot. See you next time.